To start the last session of this workshop, I have the pleasure to introduce Soheil Behnezhad, who is currently a PhD candidate at the University of Maryland, but will relatively soon join Northeastern University as an assistant professor. But before that, will spend 1 year in Stanford as a postdoctoral fellow. Soheil is broadly interested in theoretical computer science with a specific focus on the theoretical foundation of big data algorithms. And his works revolves around massively parallel computation, streaming algorithm, graph sparsification, and dynamic algorithms, among others. And he will right now talk about locality and stochastic matching problems. Thank you a lot.
Thank you very much for the introduction. I'm very happy to be giving this talk, and thank you for inviting me. So I'll be talking about locality and the stochastic matching problem, and this is based on joint works with Behnezhad and Mohammad Ajiabai. So throughout the talk, please feel free to stop me anytime that anything is unclear. And one other thing I want to mention before jumping to the problem definition and talking about the problem is that this stochastic matching problem is actually not really in the distributed setting. And in fact, the algorithm that we use for it is also completely global, not really distributed. But the reason that I decided to talk about this work at Potsy is the fact that we actually use distributed local algorithms for analyzing the algorithm in a crucial way. And I think this is a pretty cool application of distributed local algorithms. Good, so let me start by defining the stochastic matching problem. So we are given an arbitrary graph G, right? So this could be any graph, and along with a parameter P, which is a probability between 0 and 1. And then we have a subgraph GP of G, a random subgraph that includes every edge of G independently with probability P. Right? So this is a random edge subgraph, particularly. And we are unaware of this random subgraph GP, but what we want to do is to find a large matching of GP. So how can we do this? We can query the edges of G and see which one of them are realized, right? And the goal is to query few edges of G and find a large matching in GP, right? So again, we have this base graph. Some of the edges are realized, some of the edges are not realized. What we want to do is query a small fraction of the edges of this base graph and find a large realized match, right? So slightly more formally, what we want to do is to pick a degree bounded subgraph Q of G, right? So this is a degree bounded graph, much sparser than G, such that we maximize the approximation ratio. And this is how the approximation ratio is defined. It's the expected size of the maximum realized matching of Q, the subgraph that we query, over the benchmark, which is the expected size of the maximum realized matching of G. Right, so introducing some notation. So let me just use function mu to denote the size of maximum matching. So we basically want to maximize the expected, we want to pick Q such that we maximize the expected size, the expected value of mu of QP, the realized subgraph of Q, over the expected size of mu GP, which is the benchmark, the expected size of the maximum matching of GP. Good. So why is this problem important? It's been studied extensively over the past few years for its applications, mainly in kidney exchange, also in online labor markets, online dating, etc. And this is also a natural way of defining what a matching falsifier is. So basically, we want to pick a sparse subgraph such that if some edges of the graph fail, we still have a large matching of the graph. All right. So let's see a quick example. So suppose that this is our base graph G. I'll call these the outer edges and these the clique edges. So this is what a typical realization of G looks like. Half of the edges will be realized. And this is a maximum realized matching, right? So the maximum matching of the realized subgraph. And this is, say, an example subgraph that we can query, right? So we pick some of the edges of the clique, query them, half of them will be realized, and we find a matching among those that are realized. So here, this is the benchmark, the matching on top is the benchmark, and this is the matching that we find, right? So this is not really a good approximation because we are not querying the outer edges, which happen to be very important. If we also query the outer edges, what we find, the matching that we find will be much closer to the optimal matching in size, and we obtain a better approximation, right? So Good. So let me quickly start with some trivial algorithms. Before that, is there any question about the model and the problem? Perfect. Good. So one trivial algorithm is to query all the edges. Of course, we will have the optimal approximation ratio 1. Problem is, this is not really a sparse subgraph. We want to query a sparse subgraph. Another trivial algorithm is to just query a maximum matching of the base graph G. Of course, this is a maximum matching, has maximum degree 1, very sparse. Problem is, only p fraction of the edges of this maximum matching will be realized in expectation. And the graph could be such that the realized subgraph actually includes a near perfect matching. So this is only going to get a p approximation. And think of p as a small constant, right? So this is not going to be good. So this is a very natural alternative algorithm which has been studied quite extensively for the past few years. So what is this algorithm? So instead of picking just one matching, we pick multiple matchings. So the way it works is we start with graph G, we pick a maximum matching M1 of G, right? Remove its edges from G, take another maximum matching of the remaining graph, remove its edges, again, another maximum matching, and repeat this for some, say, a function of P number of steps, say maybe 1 over P steps, right? And then query the union of these matchings. So this is a very natural algorithm. And it happens to be the case that this algorithm obtains a near half approximation at least. Right? So if this parameter R, which controls the maximum degree of the subgraph that we query, is large enough with respect to 1 over P, you obtain a close to half approximation at least. But it's also known that the approximation ratio of this algorithm is not better than 0.83. Good. What I actually talk about is an algorithm that's also based on the same intuition of picking multiple matchings, but there's a subtle difference. And what is this algorithm? We again have a parameter R which controls the maximum degree, but this time, instead of picking matchings and removing them, what we do is we take independent realizations of the space graph G. So we realize every edge independently with power to P, and we do this independently R times. And from each one of these realizations, we pick a maximum matching and query the union of these matchings, right? So in particular, these matchings may possibly share edges. We're not removing the edges. We're not changing the structure of the graph. But what hopefully allows us to pick different edges is realizing different edges, right? Obtaining different realizations. Good. So again, the subgraph that we pick is going to be sparse. Its maximum degree is going to be only R, and think of R as some function of P. So it's going to be constant so long as P is constant. And we show that this algorithm actually obtains a 1 minus epsilon approximation so long as this parameter R is large enough with respect to both P and epsilon. And I particularly want to emphasize that the maximum degree of this parameter R does not depend at all on the structure of the graph, particularly the number of vertices or anything. So long as it's going to be larger than some function of P and epsilon, it's going to guarantee that this algorithm obtains a 1 minus epsilon approximation for unweighted graphs, and a variant of this algorithm also obtains a 1 minus epsilon approximation for weighted graphs. So more formally, what we prove is the following: that for any possibly edge-weighted graph G, and any epsilon, any positive epsilon, and any realization probability P, there's a subgraph Q of maximum degree dependent only on epsilon and P, obtaining a 1 minus epsilon approximation, which we define to be the expected size of the maximum matching of the edges that we query over the expected size of the maximum matching of the realized subgraph. Right? So this is the main theorem that I'm going to talk about, and the algorithm was just a simple Monte Carlo algorithm like this, right? And let me just make a few remarks. Dependence on both epsilon and P is necessary for obtaining 1 minus epsilon approximation. So this degree, the dependence on epsilon and P is necessary. So in that sense, the parameters that this degree depends on are optimal. However, the actual dependence is a little too much. So it's a triple exponential in 1 over epsilon and quasi-polynomial in 1 over P. But still, it's important to know that for constant epsilon and p, we can query a constant degree subgraph and obtain a Bauer epsilon approximation. And it remains to be an important open problem whether we can reduce this to maybe one over poly epsilon p. And in fact, we conjecture that the same Monte Carlo algorithm might get this this 1 minus epsilon approximation with poly 1 over epsilon p queries, though we do not know how to analyze it. All right. So let me tell you a little bit about the analysis now. Oh, and one thing that I want to mention here is a note that from each one of these realizations, we are picking, say, a maximum matching. And the maximum matching is not something that's local. Yet for analyzing this algorithm, we can use distributed local algorithms, as I soon talk about. So this is, suppose that this is a base graph G, and again, suppose that every edge is realized with probability half. So we take one realization, pick its maximum matching. We'll look something like it. Take another realization, maybe another half of these edges will be realized on some other edges of the clique. We add them to this subgraph that we have, and we repeat this for some function of p and epsilon number of steps, and query the set of edges that have appeared in at least one of these matchings that we picked. Good. So to analyze this algorithm, the first challenge is that these realizations G1 through GR that we choose and pick these matchings from may be very different from the actual realization that the benchmark is defined, right? So this is an independent realization. It could be very different from these realizations. And in fact, if you pick any one of these matchings, take the matching of, say, this realization GI, only p fraction of its edges are expected to be realized in reality, in the actual realization, right? So what you have to do is to prove that the realized matchings of these different matchings that we pick can be put together, maybe augment each other, and find the matchings that's as large as each one of them individually. Right? So that's the challenge. And to do this, so let me just start with the definition. So I'll define QE to be the probability that an edge E happens to be in the optimum matching, right? So if you realize a subgraph, pick a maximum matching, probability that this edge appears in that maximum matching. And suppose that whenever I say pick a maximum matching, I'm using a deterministic algorithm that just gives a unique matching, right? Unique maximum matching. Say maybe the lexicographic first one. Okay. Doesn't really matter. Right? So good. So QE is probability that each edge appears in this maximum matching. And then we define some threshold tau between 0 and 1, and which depends on both epsilon and p. And we call an edge crucial if it belongs to this optimum with probability at least tau, if QE is at least tau, and non-crucial otherwise. So if the probability that an edge appears in this optimum solution is larger than some threshold, we call it crucial because it appears in a large fraction of these realizations, and non-crucial otherwise. Okay, so in this graph that we've talked about a few times during the talk, the middle edges, the clique edges, are not that crucial. That you can maybe use them interchangeably. That the probabilities that they appear in the optimal solution are very small, so they're called non-crucial. But these outer edges, whenever they are realized, you have to put them into a maximal matching, and so they're going to be crucial. And so because QE would be close to P for these edges. All right. Now, the first simple observation is that if the number of these different realizations that we take and we pick a maximum matching from each, if this parameter R, which also controls the maximum degree of the subgraph that we query, is much larger than 1 over tau, then we nearly query all the crucial edges. Right? So every time that we pick a realization, take any crucial edge, it appears in our subgraph with probability at least tau. Right? So if we repeat this, say maybe log 1 over epsilon over tau, then every one of these crucial edges appears in our subgraph that we query with probability at least 1 minus epsilon. So we nearly have all of the crucial edges queried. But on the other hand, we can only query a small fraction of non-crucial edges. So in the clique, for example, we have n squared edges. What we can query is only O of n edges if epsilon and p are going to be constants. So this is the outline of the analysis. We would like to argue that the realization of Q has a large matching M. So in the first step, we look only at the crucial edges. We reveal the realization of crucial edges, and then find a matching MC on these realized crucial edges. And we use a specific algorithm for finding this matching. And this specific algorithm is where we use distributed local algorithms. I'll talk about this in the next slide. So this is only in the analysis. We realize these crucial edges. And in the analysis, we say, okay, there's this distributed local algorithm for finding a large matching on these edges satisfying certain properties. And then what we do is we commit the edges of this matching MC that we find on the crucial edges to be in the final matching that we're going to report, this matching M of the realized graph of Q. And then we reveal the realization of non-crucial edges. Once we reveal the realization of non-crucial edges, we find a matching among the verses that are left unmatched by MC. Right? So if an edge, at least one of its endpoints are matched by MC, we just don't look at the realization of this edge even. Okay, so we reveal the rest of the edges of non-crucial edges that we've queried and try to find a large matching amount. And then we add those two. Right? So in some sense, we're in our analysis, we treat this in sort of a non-line way. We only look at the crucial edges first. And just by looking at the crucial edges, we commit to the subset of the realized crucial edges that we will report to be in the matching, and we commit to this. And then we only look at the non-crucial edges. All right. Good. So now let me talk about the distributed local part and how we find this specific matching of the crucial edges. Excuse me. So let G be any graph, and so don't really think about the problem or the algorithm for now. Just this is a standalone statement. Let G be any graph, and A be an arbitrary matching algorithm. This could be a randomized algorithm, could have any crazy kind of correlations with how it chooses different edges to be included in the matching. We prove that there is another randomized algorithm for constructing a matching M on the realization of G, on the realized subgraph of G, such that first, it satisfies the marginal probabilities of this matching A. In other words, take any vertex, for example, the probability that our algorithm matches this vertex is going to be very close to the probability that this algorithm A matches this vertex. So our algorithm is going to be very similar to algorithm A. Particularly, this implies that the size of our matching is going to be very close to the size of the matching that A reports. But in addition, this is the additional property that our algorithm has. Take a subset of the verses in the graph. If their pairwise distance, their graph theoretic distance, is large enough, right? So if all pairs of verses in the subset are far enough in the graph from each other, whether or not the algorithm matches these verses will be completely independent of each other, right? So recall again that this algorithm A can have any correlation between verses far away from each other in the graph. What this new algorithm does is it essentially decouples these. They are matched very much independently. Yet at the same time, we satisfy all the marginal probabilities. So we prove this using distributed local algorithms. And why is this so useful? So take this as an example. So suppose that this edge E1 and E2 are crucial, and this middle edge is non-crucial. Now, if the algorithm A that we use to find the matching of crucial edges works in this correlated way, so suppose that with probability half, it puts E1 in the matching, and with probability half, it puts E2 in the matching. So we would never be able to use this edge E3 in our matching. right? But if we have independence, if these edges are added to the matching of crucial edges independently, there is a probability 1/4 that both these edges are a match, both these endpoints of E3 are a match. And in that case, we would be able to add this non-crucial edge to the matching. So this independence is very important for the analysis. And without it, it can actually be proven that no algorithm can obtain greater than 2/3 approximation for this problem. Right? So this independence is crucial for the analysis and for the problem statement. Good. So how do we guarantee this independence? And here's how we use distributed local algorithms. I'm not going to go over the details of distributed local algorithms. I'm sure that everyone here knows the definition. But just basically, we're given a huge graph. Every vertex only knows its ID initially and maybe the ID of its direct neighbors. And two vertices can send messages to each other if they are neighbors. And we want a low round complexity algorithm that finds, say, a specific match. Right? Now, if an algorithm takes R rounds, what essentially this means is that if you take a vertex, all that this vertex knows is what the vertices in its R hub know, right? So two vertices can send message to each other if they're directly neighbors. So in R rounds, what you can only do is to send a message from a vertex to the vertices in it that have distance at most R to this vertex. Right? So in other words, if we have an R round distributed local algorithm, the decision of a vertex is independent of just the decision of two vertices that are at distance more than 2R from each other are going to be completely independent. And so, and this is how distributed local algorithms play an important role in achieving this independence and proving this analysis. Although there are some challenges not really present in maybe regular distributed algorithms, particularly one is that we want to give a distributed algorithm that satisfies this given marginal probabilities. We also want to make sure that the matching that we report at the end uses only the realized edges. So we are, in a way, working in a stochastic graph, right? So the base graph is a stochastic, only p fraction of the edges can actually be used. And the third the challenge is that we want a very small round complexity to achieve this independence. And in fact, we have to avoid, say, the log star and dependence on the round complexity. It's really important that the round complexity only depends on the maximum degree of the graph, but not at all on any parameter of the number of vertices in the graph. All right. Yes, I actually mentioned this before, that these are really maximum matchings that we pick from these different realizations. So this is really a global algorithm, yet distributed local algorithms happen to be very useful for analyzing it. So to conclude, we show that the stochastic matching problem admits a 1 minus epsilon approximation by picking only a constant number of, by querying only a constant number of edges per vertex, where this constant depends only on epsilon and p, and dependence on both epsilon and p is necessary for 1 minus epsilon approximation. And the main open problem is can we actually improve the dependence on epsilon and p for this result? Particularly, the question is what is the right dependence on epsilon and p? It would be really appealing if we can reduce this to poly 1 over epsilon and p. And our conjecture is that the same algorithm should work and obtain the same 1 minus epsilon approximation guarantee with these main queries. Yet we do not know how to prove such a strong guarantee. Yeah, and with that, I'm going to conclude the talk. I'd be really happy to take any questions.
Thank you very much. So are there any questions? Feel free to either write in the chat or unmute yourself and speak freely.
So I have a question. So, so here you conjecture that this dependency is like poly of 1 over epsilon p. So somehow much better than what you get. So where do the exponent come from in your analysis? Like I don't know. Do you think you use tools that are too general, or that there is another way to do the proof, or?
Yeah, so this is a great question. So the reason that the exponential dependence occurs is really comes down to how. Okay, so maybe okay, good. So this was the lemma that we used using distributed local algorithms, and unfortunately, it's a little technical to say exactly why that exponential dependence occurs, but it all comes down to how strong the independence property is, particularly how far away the vertices need to be for their decisions to be independent, right? So using distributed local algorithms, there are lower bounds saying that, yeah, so these vertices need to be log delta away at least for their decisions to be completely independent. And this log delta dependence is actually something that cascades and leads to this exponential dependence. If, for example, we had another way of proving this independence where maybe vertices that were closer to each other were completely independent, this would directly improve the analysis and would lead to a better bound on the degrees. But yeah, but using distributed local algorithms, it seems that it's hard to get around this log delta dependence.
Yeah. Okay, thank you. I have a second question if nobody dares to, to ask another question. Okay, so my second question is, can you give kind of an intuition? I guess I kind of got it during the talk, but can you give an intuition why the previous algorithm, the one that is like whose performance is upper bounded by 0.8 something, why it is not as good? Like what's bad about it?
I see. Yeah, this is a great question. So what's really the limit with this algorithm? You know that algorithm 3 is completely deterministic. You pick a maximum matching, remove it, pick another maximum matching, remove it. But algorithm 4 is actually randomized. You're taking different realizations, and from each one of these realizations, you pick a maximum matching. And this is the key difference, right? So the example where we can show this, the first algorithm, the algorithm 3 is not better than 0.83 approximation. You start with a graph. You say, okay, so this deterministic matching algorithm that I use picks this maximum matching. And then once you remove it, this is the next maximum matching that I pick. And if you do this in a delicate way, you can only pick edges from a specific part of the graph, leaving all the rest of the vertices basically matched unmatched in most of them. Whereas if you think about algorithm 4, it's picking the edges from exactly the same distribution that the optimal solution picks its edges from. So it's really hard to, so the first, when I first thought about this algorithm, I was like, it seems impossible to give a counterexample for this algorithm because the edges are really picked from the same distribution that the optimal edges come from. So yeah, so that's how they differ. But yeah, but so the key difference I think is the way that the second algorithm uses randomization and that it picks edges from the same distribution as ours.
Okay, nice. Thank you.
May I ask a short question?
Sure, you're
so,
next speaker.
yeah. So can you use your algorithm in a weighted version of your problem?
Oh, so the algorithm can be nicely generalized to the weighted version. You take different realizations for each one of these realizations. You pick the maximum now weighted matching. Unfortunately, however, we do not know how to analyze this algorithm. We do still know the same 1 minus epsilon approximation guarantee for weighted graphs as well, but the algorithm is a little different. Yeah, so there's a little bit of technicality with analyzing this algorithm.
Yeah.
If it was up to conjectures, I'd still conjecture that the algorithm, even for the weighted case, should obtain all minus some approximation. But we do not know how to give such guarantee.
Yeah. And did you run simulations?
No, I have not done simulations because it's really hard to guess like which graphs would be hard for the algorithm.
Yeah. Sure. Thank you.
Okay.
I think we can thank the speaker again.
Sure. Thanks, Soheil.
Thank you.